Welcome back. In today's lecture, we will discuss the separation of boundary layers from the surface and about the drag on bodies moving in fluids. We had seen that in creeping flows, which are flows at Reynolds number much below 1, the characteristic pressure difference is of the same order as the characteristic shear stress. The drag on this sphere is given by 6 pi mu r u Stokes formula, of which 2 pi mu r u is because of the shear stresses on the surface and 4 pi mu r u is because of the pressure differences. The pressure is antisymmetric. The pressure at the nose of the body is positive. The pressure at the tail of the body is negative. Note that the drag on a sphere or any other body in a low Reynolds number flow does not depend on the density of the fluid. This agrees with the approximation of negligible inertial forces at very low Reynolds number. However, the conventional practice, largely dictated by the fact that most flows of engineering interest are at fairly large Reynolds number, uses inertial force 1/2 rho u square as the characteristic pressure difference and define the drag coefficient CD as drag divided by 1/2 rho u square times the characteristic area. From the dimensional analysis, we can get CD is a function of Reynolds number and the geometry. If we plot the drag coefficient versus Reynolds number, we see that the drag number decreases with Reynolds number, but at very high Reynolds number, the drag coefficient is almost constant of the order 1. In fact, its value is about 0.5. Initially, the drag varies linearly with velocity, but for larger value of Reynolds number, the drag varies like u square, since the drag coefficient is about constant. But the point to notice is that the drag at large Reynolds number, the drag coefficient is of order 1. This seems to be in contradiction with the approximations that we have learned to make. D'Alembert proved that for incompressible and inviscid potential flows, the drag force is identically 0 on a body moving with constant velocity relative to a fluid. This happens because in the inviscid flow, as the fluid accelerates from the stagnation point at the nose to shoulder, the pressure decreases. On the lee part of the body, the velocity decreases to the stagnation point and the pressure rises. Thus, the net force on the right, on the front part of the body, is being cancelled exactly by the forward force on the lee side, resulting in 0 drag, 0 pressure drag. Of course, there is no shear stresses, so there is no shear drag. It was proved later that this drag is 0 on all bodies, whatever be the shape, not necessarily cylindrical or spherical. Now, this result was obtained for non-viscous flows. In actual flows at high Reynolds number, where we have shown that we can neglect viscous stresses, the drag is not 0. And it is not surprising that it is not zero, because we are neglecting viscosity. So, in the presence of viscosity, there would be viscous drags, viscous stresses, and hence the presence of drag would not be surprising. But since in such flows the viscous forces are small compared to inertial and pressure forces, the drag must be small compared to pressure forces, or the drag coefficient defined with pressure difference as the characteristic stress should really be small. Zero drag predicted by D'Alembert is therefore in direct contradiction to the observation of drag coefficient order 1 on bodies moving relative to the fluid. It is further confusing when we note that the drag coefficient on a flat plate derived with the boundary layer approximation is about 1.328 divided by Reynolds number under the root, which again is quite small and in line of what is expected because of the approximation. So, the real D'Alembert paradox is not that there is a drag, but that the drag on a Bluff body is large, not of the order of shear stresses, but of the order of pressure forces. The resolution of this paradox lies in the peculiar dynamics of the boundary layer. That is, in its tendency to become reversed under certain conditions and to separate from the wall. This is accompanied by formation of eddies in the wake of the body. We have seen that flow behind a cylinder looks like this. This changes the pressure distribution on the wall from the inviscid one and leads to incomplete recovery of pressure in the wake, leading to drag forces of the same order as pressure forces. Thus, the separation of the boundary layer on the surface of a body makes the flow disturbed and the pressure does not recover back to its original level in the wake of the body, and thus a pressure drag results. And the pressure drag is of order 1. Thus, the drag coefficient defined the way it is of order 1. The separation occurs in all kinds of geometries, including internal flows. Flow through blades of rotary compressor and turbines are also victim of the problems caused by separation if not designed properly. Designing bodies with low drag or internal passages with small losses are attempts at suppressing separation. Consider this two-dimensional body. The flow about this separates at these 2 points. And this separation is because of a flow reversal on the surface of the cylinder. And this causes the formation of eddies in the wake. The actual flow about such a body looks like this, separating from the surface. This is another picture of a boundary layer separating from a body. This flow is made visible by applying a coat of titanium tetrachloride on the surface of the body, and when the air flows past this, it produces a smoke-like vapor, and we can see how the vapor separates from the body and creates vortices in the wake. We have seen earlier that in inviscid flow, the pressure distribution is given by this curve. The pressure coefficient is 1 at the nose. It goes down to value of -3 at theta is equal to pi by 2, which is at the top of the cylinder. And in the rear of the cylinder, the pressure coefficient is again 0.1. The pressure distribution is completely symmetrical fore and aft, and so the total drag is 0. But because the boundary layer that forms on the cylinder separates from the body, this pressure distribution changes in the rear, though in the front of the cylinder it remains as if the flow is inviscid. So in an actual flow with high Reynolds number, the pressure distribution is more like this. On the graph, it is like this. So pressure in the wake has not recovered to the value in front of the cylinder, and this results in considerable drag. Since this drag force is because of pressure forces, when the drag coefficient is normalized with respect to pressure forces, we get a value of the order 1. We show here how the velocity profile changes down a surface where the pressure is increasing in the streamwise direction. Because the flow in the boundary layer has slowed down, so the kinetic energy of the flow here within the boundary layer is much less than the kinetic energy in the main flow, that is the flow outside the boundary layer. And if the flow outside the boundary layer has sufficient energy to negotiate the adverse pressure gradient, the flow within the boundary layer does not have sufficient energy. And so the flow within the boundary layer near the wall slows down much more. Still later, the flow velocity near the surface has a 0 slope. du by dn tends to 0 at the surface. The fluid in the boundary layer close to the plate, not exactly at the plate, but close to the plate, is turning to be about 0. And a little later, because of more increasing pressure, the flow reverses. The flow starts flowing in the backward direction near the plate. Because of this, a separation occurs, and we get this as the line of separation. There is a reversed flow within the boundary layer or close to the surface. So the boundary layer that was for developing here now separates and moves this. This whole region here now is disturbed. The pressure here is no longer equal to the pressure that would have been if the flow was truly inviscid and no boundary layer was forming. Since an increasing pressure, that is dP by dx positive, leads to separation, which is not a desirable condition, such a pressure difference is called an adverse pressure gradient. And wherever the pressure gradient is negative, that is, pressure is decreasing in the streamwise direction, we call that favorable pressure gradient. We show here the typical velocity profiles and the shear stress profiles in flows with negative pressure gradient, that is favorable pressure gradient, and in adverse pressure gradient. The shear stress here becomes 0 because du by dy is 0. In this case, du by dy is positive. There is positive shear stress. Separation occurs wherever there is an adverse pressure gradient. If we have a cylinder and a flow past this, there is separation here, because if the flow was inviscid, the pressure would have been increasing after that. And so the separation takes place a little before the shoulder points. Now, if we attach a splitter plate to the cylinder, a plate in front of the cylinder, then the flow taking place in that direction, the velocity is decreasing and pressure is increasing. And the presence of this plate causes a boundary layer to develop here, and this boundary layer would separate in the presence of this adverse pressure gradient. Thus, we have the flow which is separating somewhere here on the two sides. And we have vortices formed here in which the fluid is recirculating on top. This did not happen when there was no plate, because though the pressure was increasing, there was no wall on which a boundary layer was developing. Similarly, we have this plate held perpendicular to the flow. The flow separates at this tip, because if the flow was to proceed down the back side of the plate, the pressure would have been increasing and the flow separates, forming two large attached vortices. Because the Reynolds number is not very high. If the Reynolds number was very high, these vortices would have been washed down and we would have a region of turbulence in that place. Here, we have flow in a diverging passage. The divergent angle is very large. We have this is the flow of water through the diverging passage. There is an electrical wire here in which we are passing a current so that the hydrogen bubbles are being formed. You notice that near the wall, the flow is backwards. The hydrogen bubbles formed here are going back and then being washing down. So the flow has separated at somewhere these locations. The passage is diverging, air is increasing, velocity is decreasing, pressure is increasing, adverse pressure gradient. Presence of wall, boundary layer is developing. So, the boundary layer separates in the presence of adverse pressure gradient. This is why the divergent portion of nozzles, known as diffusers, should be designed with very small divergence angle, so that the adverse pressure gradient is not too much, not that causes separation. This sketch illustrates the separation that we are talking of. At about this point, the velocity gradient normal to the wall decreases to 0 and the flow separates. We have thus separation at these two locations, and there is a reversed flow near the wall, as you can see. We have recirculating eddies in this region. Separation also takes place on aerofoils if the aerofoils are at large angle of attack. In this case, we have shown a small angle of attack. A boundary layer that developing on the upper surface is shown here by smoke streak lines. When we increase the angle, if the flow was to go around this, then the pressure would increase. And so, it creates an adverse pressure gradient very close to the nose, and the flow separates itself from the wall at the nose itself. This is stall in the language of avionics and needs to be avoided. This leads to sudden decrease in lift and a sharp increase in drag, a condition quite harmful for the aircraft. Let us now understand some interesting phenomena associated with drags on immersed bodies at large Reynolds number. There are some curious phenomena that take place when we investigate drags on various shaped bodies. In this first experiment, we have shown a sphere and a tear-shaped body, which we call also a bomb-shaped body, that is a streamlined body, exposed to a stream of air at same velocity, and these are attached to a beam at equal distance from the fulcrum. When the flow takes place, we notice that the balance is as shown, indicating that the drag on the sphere is much more than the drag on the streamlined body. This is what was to be expected. On the streamlined body, the boundary layer does not separate very much. If it separates at all, it is near the trailing edge. And so, the pressure on this body recovers as we go down, and the pressure differences in the front and the back are small. Therefore, the pressure drag is small. On the other hand, on the sphere, we have shown just now, the flow separates before the equator, and the pressure at the back of the sphere does not recover to the values in front, and that leads to large drag of the order of pressure forces. Of course, on the streamlined body, the shear stresses are more, if for no other reason, because the area of the surface is more. For large Reynolds number flow, this bar diagram show you the relative drags. The light purple color shows the pressure drag for the Bluff body and for the bomb-shaped body. The pressure drag is much smaller, order of magnitude smaller on the bomb-shaped body than on the Bluff body. Though the shear drag is larger on the bomb-shaped body because it's larger area, it still doesn't make up for the large difference in the pressure drag. And so, the total drag on the bomb-shaped body is much less than the total drag on a Bluff body. Another interesting phenomena, as demonstrated by Shapiro in his famous set of movies on fluid dynamics of drag, is a series of 4 movies made in 1960s that explore the drag phenomena. It is available on YouTube. You are strongly advised to look them up. That makes for interesting viewing. He has a large sphere which is played on by a stream of air from a nozzle below it. The drag experienced by the body is measured by this spring balance. As the air velocity increases, the drag changes. And we see an interesting change in the drag with velocity. The way shown the velocity as 0 in this graph, the velocity is not 0. We start with a fairly large velocity. The corresponding Reynolds number for the order of over 1,000. And we see that the drag varies parabolically with the velocity, like v square, signifying that the value of the drag coefficient is constant, because drag coefficient is drag divided by 1/2 rho v square times the characteristic area. In this case, the characteristic area is the frontal area of the sphere, pi r square. So, drag varies like v square, means CD is constant. Then at a certain velocity, fairly large velocity, the drag suddenly decreases. Various authors have termed it as a drag crisis. The drag suddenly decreases, but then starts increasing again. Again like v square, but this curve is lower than the initial curve. It is again varying like v square. That means the drag coefficient is again constant, but constant at a lower value than it was earlier. What is happening? What is happening is that there are two kinds of separation. When the boundary layer is laminar, then the separation takes place earlier. In this picture, it's about this case. If the boundary layer is turbulent, because the Reynolds number is larger, then the boundary layer is more energetic. So the velocity near the surface does not reduce to zero till much later down the stream. And the separation is taking place now at a much later location. This delay in separation when the boundary layer is turbulent, which happens when the Reynolds number is larger, results in a different profile. This was the profile of pressure that we've seen earlier. The pressure not recovering at the back of the cylinder. When the boundary layer is turbulent, the recovery is much more than when the flow in the boundary layer is laminar. And the separation is delayed from around here to around there. This results in a narrower wake. The pressure recovery is more than that in the case of the laminar flow, reducing the pressure drag in the case when the separation is turbulent. And this results in a lower drag coefficient. Notice that this here represents laminar separation, where we can take CD to be constant about 0.5. And then later on, when the boundary layer becomes turbulent, the separation takes place at a much downstream location, and the drag coefficient is the order of 0.3 or so. This is at about 4 into 10 raised to the power 5. Reynolds number equal to 4 into 10 raised to the power 5 on a smooth sphere. So, on a Bluff body at large Reynolds number, the total drag, which is shear drag plus pressure drag, and the shear drag is negligible, so drag is largely because of pressure drag. And for lower Reynolds number, for lower velocities, the separation is like laminar with a wider wake, and for larger velocity, larger Reynolds number, the separation is narrower with more pressure recovery and hence lower pressure drag. So, while the shear drag is larger in the case of turbulent flow, but since the shear drag is a small percentage of the total drag, even the increasing turbulence drag cannot overcome the sharp decrease in pressure drag because of a larger pressure recovery. And hence, the total drag in the case of turbulent flow is smaller than in the case of laminar flows. Now, in this picture, we have two identical spheres, except then that on the sphere on the right, we have wrapped a wire before the equator. This wire we'll call the tripping wire. This makes the boundary layer turbulent. This introduces roughness on the surface, and because of the roughness of the surface, the boundary layer becomes turbulent earlier, that is at lower Reynolds number, than it would on a smooth sphere. So there is a regime of flow, there is a regime of Reynolds number when the boundary layer on the smooth sphere would be laminar, while the boundary layer on roughened sphere would become turbulent, leading to a lower drag on the roughened sphere, as is illustrated in this figure. Because of the roughness, then, the transition has now shifted from here to here. Much earlier transition. And therefore, this is the domain in which the experiment illustrated here would be visible. In this, the drag on the smooth sphere would be larger than the drag on rough sphere, as shown here. The viscous drag, the shear drag, would be more on the rougher sphere, but the pressure drag reduces, and so the total drag is less. Now, another curious phenomena in drag is if we analyze the drag on the bump-shaped body, the streamlined bodies, and investigate the effect of roughness. Now, when we investigate the effect of roughness on streamlined bodies, we see a phenomena which is directly reversed of what we saw on bluff bodies. Here, for a certain range of Reynolds number, the drag on a roughened bomb-shaped body is more than on a smooth surfaced body, unlike in a sphere where smooth sphere had more drag than the roughened sphere. And why is this so? This is so because there is very little pressure drag to begin with on a tear-shaped body, on a bomb-shaped body. The drag is dominated by the shear stresses. So, as the flow changes from laminar to turbulent, the decrease in pressure drag is small because the drag is itself small, but decrease in viscous drag, the shear drag, now dominates. The shear stresses in turbulent flow are much more, large area, so the shear drag increases, and since it is dominating, the drag on the rough streamlined body is much more than the drag on a laminar streamlined body. That's why attempts are made to keep the flow on aircraft wings, which are streamlined, to be laminar as far as possible. The whole class of aerofoils known as laminar flow aerofoils, which have been developed for the purpose. One last experiment to complete the study of drag. Let's have two bodies, one spherical, a blob body, and one bomb-shaped body. The two bodies are designed such that the frontal areas are the same and the wet weight are the same. That is, the weight minus the buoyancy are equal. So that while in liquid, the net force accelerating them downwards is the same. Since the density of glycerin is different from density of water, the design of these bodies will be different for glycerin than for water. If we release the body in water, as expected, the streamlined bodies reaches the bottom much faster because it has lesser drag, and so the net force is more, and so it accelerates faster and reaches the bottom faster. This is as per our expectation. But when we do the same in the glycerine, here too the wet weight of the bodies are equal, the frontal areas are equal, and we see that in this case, when we release the two bodies, is the Bluff body that reaches the bottom earlier than the bomb-shaped or the streamlined shaped body. Why is that difference? And the difference is in a very simple fact, that now we have flow at lower Reynolds number in glycerine. In the glycerine, the flow is dominated by shear stresses. So this shows the drag makeup for the Bluff body, and this shows for the teardrop shaped body. Very little pressure drag, no separation, question separation doesn't occur, and again dominated by shear stress. But since there is larger surface area, so the shear stress is more, and therefore the tear-shaped body moves slower in glycerine than does the Bluff body. Very curious results. In this last picture, we show the lift developing on a sphere. You can recall from the very first lecture that we defined lift in a fluid flow as a force normal to the direction of motion of the body. In this case, a ball, a sphere with one side roughened and the other smooth is traveling in that direction. So the flow is to the right relative to this. The upper surface is smooth, so the boundary layer remains laminar, and because it is laminar, it separates earlier. On the bottom side, the rough part makes the boundary layer turbulent, and it separates much later. And therefore, a top and bottom asymmetry develops in this flow. The airstream is shifted up a little. That means a force is being applied on the fluid, on the air, upwards. And the reaction of this is a force on the sphere, the ball, which is downward. So this ball experiences a downward force, a side force. This is a force that is responsible for swinging a cricket ball. more on this in the next lecture, where we'll also discuss the control of boundary layers. Thank you.